So hi everyone, welcome to the Grothintic School. This is the third part of the K-theory series. We are going to talk about topological vector bundle today, and afterwards we'll be looking into an introduction to the basics of K-theory of topological spaces. Moving forward, we will eventually end this part with showing that K-theory is a generalized cohomology theory, with the spectrum being given by BU cross Z. Anyway, so here we are. Today's speaker is Dr. Mohit Upamanyu. He's from TFA member, TFA Mumbai, and he has completed his graduate degree just recently. Yeah. So over to you.
Actually, one correction. I
Uh-huh.
have now joined as a postdoc in CML.
Oh, I didn't know that. Congrats. Yeah. You may begin now.
Okay. Begin. Right. Let us begin. Right. So today's topic, as we know, is introduction to vector bundles. For most part, today's lecture will be fairly just trying to introduce vector bundles and nothing else, like basic operations on vector bundles and such. Right. All of these on a topological space. Like more or less, the definition is always the same, right? For any kind of vector bundles we talk about, right? So there's this base space X. For us, there is mostly be X or Y, right? So the underlying assumption will always be that this is a connected space. And nice in the sense maybe locally compact Hausdorff, or maybe compactly generated weakly Hausdorff, but also path connected. I don't think that's that important, but yeah. So nice means like maybe it's path connected or something, but this is the bare minimum assumption that we'll always carry, that it is connected and some nice in some sense, right? So okay, so now let us begin with the definition of a vector bundle, right? I'm guessing that a lot of people here have seen this multiple times, but we'll still go into the definition. Vector bundle. So let E to X be a map pi, right? So this is right. So this map pi along with the space E is said to be a vector bundle, which I'll always shorthand as VB from now on. So it's said to be a vector bundle if number one, pi inverse of a point X is a vector space for all X in X, and number two, for all points in X, there exists a neighborhood U open in X and containing, right? In other words, basically a neighborhood of X, such that pi inverse of X of U is isomorphic to X cross X cross V, right, such that this map is pi. Oh no, not X. What am I writing? U cross V, such that this map is pi and this map is uh, just the first projection, right? And this diagram complex. Anything else? Oh, right. Such that another condition that we need to put is that phi is linear for all restricted to every fiber. When restricted. Okay, so that's that. So that's the definition of a vector bundle. Right. So let's do some examples. Right. So these are probably the most commonly seen examples we know. So let's start with perhaps my favorite, which is trivial vector bundle. So if X is a space and W, like X is a topological space and W is a vector space, then X cross W is a vector bundle over X. So this is called a trivial vector bundle. And as we can see, like right in the definition, every vector bundle is locally trivial. Like that's written right in the definition. Locally. Okay. Oh, also I forgot to share the link. One second. So I have just sent the Jamboard link, right? So if you need to go back and forth and look up what has been written, you can open that link and do it. And just follow along on that Jamboard as well. So another example of vector bundle would be, I don't know. So let's just say cylinder, right? So cylinder is basically S1 cross R, right? And I completely forgot to mention that uh, the field that we'll be using for vector spaces will be either R or C. So I'll usually write it as F. I'll write it as F, and that means like it could either be R or C depending on the situation. So a cylinder would be S1 cross R, but this is, as we see, a trivial bundle. So a non-trivial example would be Mobius bundle. So basically, it's like Mobius strip. I'm not very good at drawing a Mobius strip. So it's like Mobius strip, but you know what? I'm not doing this. I'm not drawing. So right, a Mobius strip, but with like infinite lengths, so that it's actually a vector space, right? That is an example of a non-trivial vector bundle that we know, right? So Mobius bundle is an example, and a third example that I would like to give, which could be trivial or non-trivial, depending on the situation, is if M is a manifold, we have the tangent bundle of M, which is like, which is a more classical example of, right? So if this was a complex manifold, we'll end up with a complex vector bundle. Right? Just want to point that out and let's proceed. So any questions? So now a lot of relevant definitions with respect to all of like useful definitions that with respect to vector bundles. If anybody has any questions, feel free to ask at any time. Right, so a morphism of vector bundle of VB, right? So E to F, right? These guys are VBs, right? A morphism, let's call that F for now. Right? They is said to be a morphism if number one, this diagram commutes. Number one, commuting of this diagram. Number two, F is fiber-wise linear. And of course, number three, F is continuous. Right? So that's one. Right? What's a section of vector bundle? Right. So a section would be something like right. It's a map from X to E. Right. Of course, E was a vector bundle. Right. X to E such that phi compose S is equal to identity. So it's like, yeah, we just had a map like this. In the reverse direction is called a section, right? Gamma E denotes sections of E, set of all sections of E. Okay.
Um,
So,
Dr.
yes.
Mohit, can you explain the second point? There is a question in the chat. It says, can you explain the second condition?
Oh. Second condition, fiber-wise linear or line. Sorry, fiber-wise linear. So what it really means is that remember that for a vector bundle, Ex for every point, the fiber above that point is a vector space, right? And the first condition says the diagram commutes. So that means the fiber above X, like of E above X and F above X will map to each other. Since both are vector spaces, we demand that that map be linear. So that's what the condition means. Right. So now and finally we define pullback. if y to x is a vector bundle, is a map, right? And y is a vector bundle, then we define f upper star of E to be the fiber product So in some sense, we have this diagram. So we define the pullback as the fiber product. That's quite literally the definition, right? And what I want to point out is it's like just using this definition, it's fairly easy to see that the pullback of a vector bundle is a vector bundle. What we need to check is that things are locally trivial. And so to check that things are locally trivial, all I need to do is that given any point P, uh, right, we want to just, so, okay. The way to see that this is a vector bundle is just saying that if U is U inside X is a neighborhood on which E is trivial, okay? If
Dr. Mohit, maybe you can just explain what a fiber is in short. I think some of them do not
oh,
understand this term.
what is a fiber product?
Maybe briefly.
Okay, sure. I'll just write the definition. It's a set of all points. Let's say X comma E comma Y such that what were the name of the maps? F and pi, right? So this is pi of E is equal to f of y. So the collection of all such points is defined as the fiber product. So, okay, so if we just go from here, we see that if E is trivial, right? Well, being trivial, remember, was X cross vector space. Then when we take the fiber product, like I'll leave that in as an exercise, we'll end up with Y cross the same vector space. Okay. So what is now going to happen is if E was trivial on if is tree or even on some U open in X, right? Then the fiber product, right? Then F star E is trivial on F inverse of U, which again is open in X in Y. So this ends up proving for us that Y is the pullback is also a vector bundle simply because pullback of trivial is trivial, right? And locally was trivial, so open neighborhoods pullback to open neighborhoods just by continuity. So operations on vector bundles. Okay. So I'll just define some notation. Let vec be the category vector spaces. Be the category of vector bundles over X. Okay, so these are two categories that we have defined, right? So roughly what we are trying to say, like what we are like what we aim to prove just now, is that like kind of like how we can take direct sum of vector spaces. In a similar fashion, we can extend these operations like direct sum, tensor product, right? Dual, right? We can extend all of these operations to vector bundles, right? So we could take direct sum of vector bundles, tensor of vector bundles, and dual of vector bundles. Like, oh, remember, like wedge I of vector bundles would lead to like like basically all alternating product of vector bundles also we can take. Basically, all kinds of operations that we have on vector spaces can a lot of them can be translated over just to vector bundles. So for this, I will kind of try to give a very general proof via category theory, right? So let tau be a functor, right? Uh, whether is there anyone who doesn't know the definition of a category? In which case I could break the proof down to earth. Or should I just assume people know category and proceed?
Yeah, you can proceed, I think.
Okay. If if T is a functor from vector spaces to vector spaces, such that the map home V comma W to home TV comma TW is continuous. Remember, the fields we have fixed to be real or complex numbers. So as a consequence, we want, so these home themselves, also I should add, we will be working over finite dimensional vector spaces. And therefore the category vector bundles that we'll have is also will be made up of finite dimension. Like the vector spaces will all be finite dimensional, right? Involved in the vector bundle, right? So just going to point that out. This is an underlying assumption which I completely forgot to mention before. So suppose home V to W is continuous. So again, these home VW, all of these have topologies, right? So now what we want to say is that we can extend this T to all of vector bundles, right? So step one is just to brutally define what the set is. So we would like to define, so if E is a vector bundle, right? So that means it's in vector X, right? Then we would define TE to be equal to disjoint union of X in X, right? T of EX, like just take. So for the moment, people should think of this like, right? Think of T as being something concrete, maybe dual. So we're saying just take the dual of every one of them, every vector space which is in the fiber, and take the disjoint union. So this
Um,
is the set, right?
Dr. Mayuk, there is a nice question in the chat box. It
Okay.
asks, what's the topology on home V comma W?
So the topology on V comma W. You, okay, I'm at the moment thinking of them as matrices. So just n cross m matrices. Like so, that's like a vector space, and so that has a topology. It's a finite dimensional vector space. I specifically restricted myself to finite dimensional just before, so that the topology is like the nice topology. Like it doesn't matter which norm you take, it's always the same topology, right? So it would be something like this would be some R NM or CNM, right? And so that gives us a topology. Okay, so let's proceed. So now E is a vector bundle. So we define the set T of it directly just by saying, okay, take all the fibers, which are vector spaces, apply the functor on them. So if the functor was dual, just take dual of all of them. Right? Take the different union, you'll get a set. Right? But a vector bundle is also a topological space. So now what we are left to do is to define a topology on it, which is nice. Right? Now, something to expect at least would be to say that, okay, if I start with something trivial, I should get something trivial. So, case one, uh, if E is trivial. So now the aim, give a topology. If E is a vector bundle, sorry, if E is trivial, that's the case we're working with. E is trivial, right? So that means it's like X cross V, right? For some reason. Then we just define TE to be X cross TV. Nothing special here. Right? More importantly, what we're really trying to do is extend the functor. By that we mean if I have a morphism between E and F, I want to extend that to a morphism between TE to TF. So that means if I had some other F, which was say X cross W, right? And suppose we have a map from 5 from vector bundle homomorphism from here to here, from E to F. Then this gives us a map from like, so it basically is a map from X cross V to X cross W, which makes this diagram commute, right? So, but if this diagram is basically being making commute, then I might as well just be giving a map from X cross V to W, right? That's more than enough data because P comma V will end up going to P comma whatever it goes to. but the P has to be same because the diagram commutes. So this data remains the same. And in particular, wait a second. Okay, that's fine. So it's enough to give a function like this. And once we get a function like this, since we also know it's fiber-wise linear, I can then proceed to say that this is same as giving a function from x to home VW. Right? If I'm giving a function like this was phi, this gave us something intermediate, let's call that phi tilde, then we get something called phi star, right? Now we know that the functor is continuous, right? It has this property. So we use that property and compose this, right? We can now backtrack all of what we just did, and basically these steps, we will backtrack them, but with TV and TW to get a function from this to x cross TW phi. And this will be called T phi. So in this way, we have extended the functor at least to the trivial bundles, right? Now, if E has two trivializations, the topology given to E is the same. I won't prove this, but the point is that the topology that we have. So if E was isomorphic to trivial bundles two-way, that doesn't quite matter. The topology E will get is the same, and that's more than enough for us. So at least the topology we have gotten is well defined. That's what we're really going for. Now, if E is any vector bundle, we know E is locally trivial. Like, so we can in fact find an open cover on which it is locally trivial. So, right. So let U alpha be a cover E is trivial. Then, you know, we define V subset of E to be open if V intersected with EU alpha, right? Oh, I forgot to mention that. Okay, EU alpha means pullback along. It's a pullback along the inclusion. Or if we have any map, we denote the pullback using. So F upper star of. So remember we had this thing. Then I could pull back the vector bundle like this, right? So yeah. using the fiber product. Here what we are doing is that we are going to pull back the vector bundle using the inclusion map. And such a pullback will always denote, we can always also denote by EY instead of F upper star E. Just a notation which I forgot to mention. And now I'm suffering because of it. Right. So this is the pullback and good. So we have a pullback here. So when B is intersected with pullback, wait, you know what? I'll erase again. Alpha is open for all U alpha. Right. So we're saying that when intersected with all these neighborhoods, minor topological or trivial neighborhoods, which is independent of where it came from, how it came from, which is what we discussed before. So when intersected with any of these trivial neighborhoods, if intersected with all of these trivial neighborhoods, so V happens to be open, then we declare V to be open. So this is how we topologize a vector bundle. Right? Now suppose we had a morphism E to F, right? Then if you wanted to check if, say, the same morphism from TE to TF happens to be continuous, really, because it's clearly linear and it will make the diagram commute, right? So the most difficult problem is, does it happen to be continuous? And so if we just happen to ask that this is continuous, to check continuity, what we'll be forced to is to look at it locally. But locally, an example of an open set, as defined here, would be just some trivialization U alpha cross V, and similarly. But for trivial vector bundles, we know that this mapping is continuous. The topology that we have given is continuous, right? So therefore, the mapping is already continuous, and so we have successfully extended the functor to the category of vector text. Basically, from vector spaces, we have successfully extended the category to the functor to all vector bundles over X. And right. So examples. So one more thing is here. Let me just go back to the theorem. Yeah. So the aim was to extend things like this, right? But in the hypothesis, I assume this is like a normal functor, right? Covariant functor, in fact. But more or less the same arguments will go through even if it's contravariant. So V dual will be taken care of. Things like the alternating product or symmetric product, right? They will also be taken care of. Those are actually taken care of this theorem. For direct sum, what we'll have to do is we'll have to take two vector bundles and take simultaneous trivializations. But otherwise, the exact same arguments go through, right? So there's nothing real, like nothing complicated happening here. Like to extend it to these other cases, right? But by doing this, we have now successfully managed to extend direct sum, right? A tensor product, dual, and all of these things. And finally, one more point to note is that the old natural map that we had before, like E tensor F is isomorphic to F tensor E, end up extending to all vector bundles because these map obviously existed fiber-wise. There is no question about, no doubt about that. And what we'll need to do is check the continuity locally. But for trivial bundles, so to check that these natural maps are nice and continuous, we just need to go locally and check that locally this condition hold for trivial bundles. So that's all we really need to do. So these natural maps that we had, like commuting tensors, commuting direct sums, associativity of tensor, tensor distributes over direct sum, all of these we can check fairly easily. And they all of those natural identities will end up extending to these. Right? So something
Hello?
like F10. Hello?
Yes. So, where in here did we use the fact that the underlying space in underlying field is the field of real numbers or complex numbers?
Oh, to get a topology on home.
I see.
Yeah, to get a topology on home. Otherwise, you wouldn't be able to. And then we utilize the topology of home to define a continuous vector. Otherwise, things would vary weirdly, and then we wouldn't get uh, vector bundles. Like if they do not vary continuously, then we don't end up getting vector bundles. That's kind of the idea. At least continuous vector bundles. If you want differentiable vector bundles, you would want the functor, like the map that it induces, to be differentiable. If you want differentiable, if you want analytic, you will want that map to be analytic, and so on.
Okay.
Okay, thank you.
Isn't it that what goes more into is that while defining a vector bundle, you are actually using the fact that like locally they're given by products of E cross K to the power N, right? So this has to be
Yes, yes, yes.
topological, right?
Yes, yes, yes. That totally goes into it.
Yeah.
But another thing which is going into it is like things like direct sum, which like is kind of hidden, is that things like direct sum and tensors happen to be nice with respect to everything.
Yeah, sure.
So it doesn't, like another thing that goes into it. Right. I mean, local triviality is like the definition, so it has to go into it somewhere, everywhere, not just somewhere. Theorem. So let's just go here. So, and another observation theorem, whatever we want to call this, right? So in a same split, if we can define tensor, we can also define home E comma E, right? So theorem is sections of home E comma E correspond bijectively to homomorphisms of E to F. So, whatever. Okay, so right. So one thing to check is like, okay, if we want to prove this theorem, does it hold for trivial bundles? Right. So we kind of proved this in the case of trivial bundles, where we saw that if E and F both were trivial, then X cross V to X cross W having a homomorphism, right? This was same as having a map like from X cross V to W, just that no other, nothing else. And this is same as having a map from X to home of V comma W. Okay, which as an extra step is a section of home X V cross V comma W. Any questions or something? So, right. So this is like this we kind of understand. Now, to complete the proof, what we do is we take the map from right. So we can define a map from gamma of home E comma F to a set of all homomorphisms vector space homomorphisms and where is it? Oh, sorry, the direction. Okay, I'm going to define a map in the reverse direction. Please don't kill me for this. Right. So if I have a homomorphism from E to F, what we can do is we take that homomorphism and we evaluate it on X. We look at what is the value above X, right? And we send it to X goes to phi of X, just the value above X, right? So phi of, yes, just this. Yeah. So this is the definition of right. And the idea is that this map, when we go, restrict ourselves to trivial neighborhoods, this map becomes an isomorphism, right? Now, another thing to note is that using this, just the fact that it becomes isomorphism, this map itself is the isomorphism we discussed above, right? When restricted to trivial gains, will now allow us to glue all of this data back to conclude that everything would be all of these, even if things were not trivial, would be an isomorphism. So that's that. So any questions? Because I'll move into the next part now. So this should be relatively easy in comparison to what we just went through, right? So at least relatively concrete. So sub bundles and quotient bundles. Right? So definition, right? So so an injective mapping of vector bundles would be a map which is injective, right? Something very obvious, right? In a similar spirit, a sub bundle which we denote by E to F is a so E subset of F is a sub bundle if number one E is a vector bundle Number two, Ex is a subset of Fx is a subspace, like vector subspace. Okay, so now one obvious statement, I don't even want to call it lemma. I don't know why I've written that as a lemma in my notes. Observe, image of a injective map is a subpattern. Right? Okay, so nothing complicated, like just that. Right? So now the direction in which we are proceeding, at least for maybe the next 10 minutes, would be basically if we have a subbundle, can we define a quotient? So could we do something like this, that we take a disjoint union of fx mod ex, right? Give this an appropriate topology, which as it turns out is the quotient topology, and prove that it is locally trivial, right? In particular, can we, if we have a subbundle, can we define a quotient? This is all we are really asking here. Aim, define quotient. Okay. That's a aim. So for that, we will need a lemma. If E is a subbundle of F, then locally we can choose a complement. Okay, so how do we choose a complement? If E is a subbundle of F, we can locally choose a complement. So again, since if the aim is to locally choose a complement, we might as well work locally, like, and locally on X, of course, right? And like, okay, what do we mean by complement? Just recall that the complement here, I mean, if Ex is a subspace of Fx, then what I mean, what I want as a complement is a complementary subspace. So what I'm saying is that on a neighborhood, I can choose a complementary subspace. Neighborhood of small x. Right, for every small x. Right, so since the statement is local, we could assume that E and F are trivial. Right, so X, so this is just some X cross V to X cross W, subset of X cross W. right? Something like that. And of course, we might as well assume it's an injective mapping, nice and injective mapping. Then what we do is we have this point X in mind, right? For that X, we choose, right? We choose a complement of V. Like so, right? For that small x, we choose a complement V prime, right? And now we have X cross V prime, which just sits inside X cross W, right? Right. So, and I'll just write this properly. Choose V prime to of Vx Wx, right? So that's what we do. And this is just the obvious inclusion of X and V prime to W, right? Now we can take these two maps and create a new map from the direct sum to X cross W. Since everything is trivial, we could just reduce to, we know that this map will boil down to V direct sum V prime. So form of this to W. But note, this point sends X to an isomorphism, right? Because V prime and Vx are complementary subspace. The small x goes to an isomorphism. In particular, this mapping, whatever, if X goes to an isomorphism and the set of all isomorphisms is an open subset, right? GLV is open in M and V, and then isomorphisms is an open subset. We immediately see that this says that there is an open neighborhood in which this map must be what is it called? This map must be well defined. No, this map must be isomorphism. So there is an open neighborhood of X on which this is an isomorphism. That means for this smaller subset U, which is inverse image of these isomorphisms, we have found a complement, which obviously contains X because X was in the isomorphisms. U to be phi inverse of iso. And then we have a consistent complement, at least in a neighborhood. Right? So a consequence of this, so everybody with me till now?
Yep.
So yep, okay. So a consequence of this is if E is a subbundle of F, then we have already seen that we can define disjoint union of this, right? X in X, right? And then give this the quotient topology, right? And we call that F mod E, right? Now what we are saying is that given an X, there will be some neighborhood U for which we have a consistent complement of E, right? But if E is a consistent complement, then what we know is that Fx mod Ex is isomorphic to a complement of Ex, right, in a neighborhood, right? And the complement that we found locally was in fact a trivial complement, right? So, like as in trivial, as in a trivial vector bundle. So it's not just for you, but it's in a neighborhood of X, right? So it's not just for a small x, it's in a neighborhood of X, and it was trivial. This implies that F mod E is a vector bundle. So we have now defined a quotient vector bundle, right? So now, because where it is, yes. So now a lemma, important lemma, right? Let E to F be a constant rank map. Okay. Then number one, we could take kernel at every point, right? So kernel of phi x, x in x is a vector bundle, right? So kernel of such a map is a vector bundle if it's constant rank. Number two, image of such a map is a vector bundle. Number three, co-kernel right? So let's just say that this co-kernel is in fact equal to f mod image, right? F modulo the image. And therefore, we immediately just see that 2 implies 3. Right? Also note that this is not an arbitrary homomorphism between vector bundles. This is a special kind of constant rank map only. Like this is a bit of a problem with vector bundles that they are not very they don't behave very nicely if we take all homomorphisms.
So what is the constant rank map?
Okay. So remember, so we have Ex. So it's a vector bundle, right? So like both are vector bundles. So that means for every fiber, there's a vector space homomorphism, right? Ex to Fx. Now for every point, we have a vector space homomorphism. So for every point, we have a rank, right? So what I'm demanding is that for every point, that rank is equal. That's what I mean by constant rank map. That for every point, the map from Ex to Fx, like the map between the fibers, has the same rank. Doesn't matter where it is. And of course, X is connected. Like that's like the hypothesis we have been assuming forever. Like if it's not connected, then we have to make like argue with every connected component separately. And so it always boils down to just proving things are connected anyways.
All right, go ahead.
Yes, sorry. Right. So we want to prove, okay, so first we have already seen that 2 to 3 is a 2 implies 3 because uh, we know that the point is image is a vector bundle and therefore a sub bundle. Right. So and as soon as it's a sub bundle, modular sub bundle will which gives us co-kernel is a vector bundle. So 2 implies 3. Now we'll also see that 3 implies 1. Right. So we just say that okay, kernel right is equal to co-kernel of F dual to E dual dual. Right. And this basically shows us that the kernel will also be a vector bundle. And also sub bundle because again linearity on the fibers is guaranteed. Right. So all we really need to prove is that so for 3, see this, right? So we really just need to prove 2. Right. And here also we'll use more or less the same complement trick that we used before. Right. So again, because we're trying to show something is a vector bundle, we want to show that they're locally trivial. Right. So showing a vector bundle is locally trivial will be like x to x cross w, we have a map. Right, so since we are talking locally, we can assume both vector bundles are local. Right. Now, choose v prime, right, to be a complement of v. Right, so this was same f phi, right, and this was E is equal to this, F is equal to this, because again we are trying to prove things locally. F is equal to this, and so suppose v prime is a complement of v. Right, sorry, complement of v x. So complement of let's be very clear, this is important, of kernel of phi x in v, right? So we choose v prime to be complement of kernel phi x. This is important that we're choosing the complement of the kernel, right? Now what we see is again there is this obvious inclusion from here to here, since after all v prime is a subspace. Right. What we note is that let's call this composition psi. Right. We note that psi is surjective on the image. At x, like only at x, because that's where we chose it to be the complement, right? Now, what you need to do is you need to notice that what is it? Right. That rank of phi y is always going to be greater than equal to rank of phi x in a neighborhood. Like for a small enough neighborhood, this will always be true, right? Why is this? Again, because of more or less the same thing, like how we saw that isomorphism is an open set. For the same reason, because rank is upper semi-continuous in home v comma w, we get a similar result here. The exact same rank. Basically, because x2 is this, so we get some kind of upper semi-continuity here itself. Right? But rank of phi, we know that this is a constant rank map. Right? So that means in a neighborhood, it has the same rank. But in a neighborhood, it can at most increase, it won't decrease. So in a neighborhood, like, so what we're trying to say is that in a neighborhood, it has the same rank, right? So V prime is mapping isomorphically onto the image. Actually, I should say isomorphically, not just surjectively, since it's complement isomorphically. And in a neighborhood, the image doesn't increase the dimension. We'll end up with the property that V prime ends up mapping to everything with the exact same dimension, at least in a neighborhood. Therefore, x cross V prime to x cross W is, what was this? Right, is a injective map isomorphic on the image. In a neighborhood. It's only in a neighborhood of x, in a small neighborhood of the point x. Right, this injectivity in isomorphism. Therefore, we can conclude that this is a image is a subbundle. That's it. So that finishes the proof. So a lot of statements. Right. So any questions? Or else I'll move on to the last topic. Any questions? Okay, so I'll begin. Right. So a projection operator definition. Right. A map P from E to E is said to be a projection if P square is equal to P. Now, a point to note that immediately this constraint will say eigenvalues are 1 and 0 only, and nothing else, right? For basically every single fiber will get this, right? Another thing to notice is that 1 minus P, the whole square, is equal to, we can just expand this out, identity minus P will itself be identity minus P, right? So I'm going to write this as 1 minus P from now on. Right? And again, this thing therefore also has eigenvalues 1 or 0 in the same matrix, right? In the same. So basically, it's like if P is 0, 1, 1, 1, 1, then this would just take the complementary eigenvalues. As a consequence, rank of P plus rank of P at X at any vector space plus rank of 1 minus px is equal to rank of the vector space E, or rather dimension of the vector space E. Right? Now remember, we also proved, I didn't write it as a separate lemma, but we did prove rank is upper semiconductors. So the rank of this will increase in a neighborhood, while the rank of this will also increase in a neighborhood, right? But there's some, irrespective of where, like which point it is always like is always the same. It's a constant. Therefore, since both are at least in the neighborhood increasing functions, upper semiconductors, but their sum doesn't increase. Therefore, we see that rank of px is constant. Right? And basically, like vector spaces, now if we have already seen in vector spaces, what happens is that uh, if we had a vector space and a projection operator like this, v of p direct sum 1 minus p of v is will be equal to v itself, right? The vector spaces which are the image of p and 1 minus p are complementary vector spaces, and that's it. That's what. So a projection operator is very good at figuring out the vector space and given a vector space and its complement, you can easily get a projection operator and vice versa. Like given a projector operator, we can retrieve back the complementary vector space and that and p and the subspace. So as a consequence, this projection operator becomes a very convenient way of finding complementary vector space, vector subspaces. But okay, but since it has constant rank, p, right, constant rank. So now I'm moving into vector bundles. We'll see that p of e is a subbundle because constant rank map images have subbundle. Similarly, the other guy also is a subbundle, right? And the direct sum will be the whole of E itself. So a projection operator now becomes a tool to figuring out global complements of vector bundles, right? But if we have seen, if again inspired from linear algebra, the easier way of getting global components is by using what is it called, inner products and metric spaces, right? And then using what is it, like orthogonal projections to get these projection operators. Okay, so a vector bundle has a metric, right? So now we move into metrics, right? So I'll just, before I like say where is this thing going, I'll just explain what we are trying to prove is that the final statement is that given subbundle E of F, there exists a complement, a global complement. right? So this is what we are aiming for. And for that, what we are going to do is create a global metric for every vector bundle, right? So first, let's define what's a metric, then it will become clear what we are saying. So metric. So it will basically mean a Hermitian metric if we are working with complex numbers, and otherwise a like not like just a normal positive definite semi-linear form in case of real numbers, right? So first, what we want to do is that for every EX, we assign an inner product, like either Herm EX in case of complex numbers, Hermitian form, otherwise just a symmetric bilinear form. Bilinear in case of EX, right? In case of real numbers. Okay. So for that, for the moment, I'm going to call it both of them Hermitian. Okay, since the proof is essentially the same, it's just the name which differs. Right. So we'll get okay. So for every point we want to assign a Hermitian metric, what we can do is we can take the vector bundle Herm E, right? Oh, sorry. X. Yeah. What is this vector bundle? Remember, we did it for we given any vector bundle, we created and a functor on vector spaces. We could just apply that functor on vector bundles. In the same way, we do this, right? And now for every point, we just want a section, right? So definition, a metric is a section from X to right? So for every point, we are choosing a Hermitian bilinear form in case of complex number and just a normal bilinear, symmetric bilinear form in the case of real numbers, right? So, but I'm still writing Herm because I just want to do it once, right? And now that if we have a metric, one thing that we can easily do is just suppose let F have a metric and E is a subbundle of F. Then what we can do is we can just take E perp. What is this? This is take the perp pointwise, right? And note that E perp will be isomorphic to E modulo, sorry, F modulo E. And in particular, this will show us that it's a vector bundle, right? So for every point, we take the complement using the metric that we have at that place, right? So this allows us to create complementary spaces, giving a metric. So final statement is that take care. If F is a vector bundle on a, so till this point, whatever arguments we have given are very general, and we haven't actually used topology much. This is the first and the last, like first and the final time in this talk, we are going to use a topological argument to show metrics exist, right? So if F is a vector bundle on X, and here I'm going to assume for simplicity compact Hausdorff and of course connected, right? On X, if it's a vector bundle on X, then F has a matrix. Okay. So why does F possess a metric? So oh, I think I forgot. Oh yes, this is a section such that uh, S of X is positive, definite. Yeah, this needs to be added, otherwise we won't be able to do things properly. Sorry for that. So if F is a vector bundle on X, then F has a metric. Like, how do we prove this statement? Okay. Is it true for, so first, can we construct it locally? Answer is yes. If it's trivial, then we have a metric on the space and we just take the same metric everywhere. So on X cross V, you just take the same metric on every single V and we are done, right? So for system metric. Now, because the space we have is compact Hausdorff, right? This implies compact Hausdorff implies partitions of unity exist. No, sorry. Right. So first step is choose a trivialization. Like, no, sorry, not as trivialization. Choose a covering U alpha such that F U alpha is trivial, right? Then, because the space is compact Hausdorff, we have partition of unity. Rho alpha, right? And I have 2 minutes and I'll finish this. Right. So now that F is trivial, what we can do, right? We can choose matrix metric U alpha, right? For each one of them, we can choose a Hermitian metric called H alpha, right? Then summation rho alpha is a Hermitian metric. Right? So just to recall, a partition of unity is our function such that summation rho alpha is equal to 1. And since summation rho alpha is equal to 1, what is really happening is we are taking a convex combination of Hermitian metric, and that represents the Hermitian metric. So this is it. We have proven that every vector bundle has a complement. Every sub-bundle has a complement, which can also be stated. I'll just say that if we have a short exact sequence of vector bundles, then this splits. Then every short exact sequence of vector bundles splits.
All right. So are we done now? Hello?
Hello, can you hear me?
Yeah, now we can.
Oh, okay. I got worried for a second. Okay, so I'm done. One second. Can you explain what is a
So
metric?
yeah.
Right. So can you explain what's a metric for a trivial bundle? Okay. So you know what's a metric for a vector space, right? It could be a positive definite symmetric bilinear form or a positive definite Hermitian form. Okay. And now that we have a metric, what we just do is, since it's the trivial bundle is just X cross V, it's the same vector space everywhere. We choose one metric and just take that to be the case everywhere. That's it.
Does that clarify your doubt? Okay,
Hmm?
cool.
Okay.
Um, are there any other questions? Okay,
Right.
there seems to be no other question. I wanted to ask one more question though. So basically what you did is given a functor from vec to vec, you essentially
Yes.
extended it to the
Yeah,
category
yes.
of bundles, right?
Yes.
So for example, you defined this home functor and the tensor functor even for bundles. So my
Yes.
question is, does the adjunction lift as well?
Yeah. All kind of natural isomorphisms will also end up lifting.
Okay. Okay. Cool.
Primarily because the moment it's a natural isomorphism, we know that it's true fiber-wise,
Mm-hmm.
and then all we are going to check is continuity on trivial vector bundle. Like we just need to check continuity, and then for that we just need to check the continuity on trivial bundles, because that's how we define the topology.
Okay. All right. So then we end the session here. We'll see you next week at the same
Okay.
time. Thanks for
Yes.
the lecture.
Thank you.
Kindly share the notes with me.
The ones that I just sent, or the ones that I wrote down the notes before the lecture. Like I had.
Either of them.
Okay.
Like whichever you feel is in the best condition.
Sure. I'll edit the notes that I have and then I'll send it.
All right. Thanks a lot.